Welcome to the lecture of CMOS Inverter. In the previous lecture, we have seen NMOS Inverter and before that alternative pull-ups. There we have compared NMOS Inverter with CMOS and we have concluded that CMOS Inverter is better for the power dissipation wise and output logic swings wise. So we are going to see in detail of this CMOS Inverter. In this lecture, you are going to understand CMOS inverter operation, its construction and its characteristics. The contents of this lecture are CMOS inverter circuit and its operation and its characteristics and sizing of both PMOS and NMOS transistors to get the symmetric VTC. The construction wise, the circuit is look like this. Pull down transistor is NMOS, pull up transistor is PMOS transistor, and at the both gates input is applied at the both gate terminals, and at the both drain terminals Vout is taken and PMOS source is connected to VDD, NMOS source is connected to the ground value. So by having of this connection, we can get the inverter action with one input. Since inverter is having only one input, so this is acting as the inverter. So pull up device is always PMOS transistor and pull up down device is NMOS transistor. Let's see its operation of the CMOS inverter for both input values of logic 0 and logic high. First, let us take Vin is equal to logic high in the CMOS inverter. What is the circuit of CMOS inverter? As the pull up, PMOS. As the pull down, NMOS. It is connected to the ground and VDD. And output is taking from the drains. Same input is connected at the both gates. Now, when Vin is equal to logic high, transistor T1 as NMOS and transistor T2 as PMOS is represented here. And for when Vin is equal to logic high, T1 is on and T2 is off. Then its equivalent circuit is represented like this: on transistor and off transistor. Off means transistor is representing as open, on means transistor is representing as the short. Then output is having a path of the pull down and there is no path to the pull up. Therefore, output is having a value of logic 0. So that means when Vin is equal to logic high, NMOS transistor is on, PMOS transistor is off. Therefore, output is equal to 0. Next, when Vin is equal to logic 0, that means if logic 0 is applied here, T2 is on and T1 is off. Since PMOS transistor is on for the logic 0, NMOS transistor is off for the logic 0. So, for logic 0 input, T1 transistor NMOS is off and T2 transistor PMOS is on. Then equivalent circuit is representing here as the off transistor and on transistor. On transistor is representing as a short path and off transistor is representing as open path. Therefore, output is having a path to pull up, not to the pull down. So, the output is reached to the VDD. So, output is equal to VDD. Therefore, when Vin is equal to logic 0, Vout is equal to producing as VDD. And when Vin is equal to VDD, it is producing output as logic 0. So, based on this truth table, we can tell this is using as inverter or simply NOT gate. And because of having the PMOS in the pull up, it produces full logic VDD, and because of using the NMOS, it produces full logic 0. So both values are full swings. And in these two cases, we can observe that one transistor is on for the one type of the input. For logic 1, pull down on. For logic 0, pull up on. So there is no rail to rail connection for the both inputs. Therefore, static power dissipation is 0 in this inverter. So static power is 0 in this inverter. Let us see the static behavior of this CMOS inverter. First, noise margin. Noise margin is high and it is equivalent to supply voltage. That is, noise margin is very high. And it is ratioless logic level, means output values of VDD and logic 0 are not the function of the sizing of the transistors. So therefore, it is independent of sizes, independent of sizes of the transistors, that is called as ratioless logic, and low output impedance, therefore less prone to the noise, and high impedance, so therefore improving the fan out, and no static power consumption since there is an open connection in the circuit. That means no direct connection between two power rails for the input of 0 and 1 values. Let us draw transfer characteristics of this CMOS inverter. When Vin 0, that is input 0, output is equal to VDD, and when Vin is equal to VDD, output is equal to 0. Okay, but in middle, when 0 is changing, input is changing from 0 to VDD, output is changing from VDD to 0. How these two are appearing from these transition regions? Let us check the total characteristics. That means, so here input is taking as 0 to VDD in middle 3 other points. To understand the transfer characteristics by taking the different values in the input, let us take some points as Vin is equal to 0 case, then Vin is equal to VDD case, that is 0 case, VDD case, and middle value, that is Vin is equal to VDD by 2 case, and Vin is equal to 0 to VDD by 2 case, and VDD by 2 to VDD case. So Vn is 0 to VDD by 2, and Vn is from VDD by 2 to VDD. Therefore, taking as 5 regions, region A is when input is equal to 0, and region B is input is from 0 to VDD by 2, and region C is from at VDD value, and region D is from VDD by 2 to VDD, and region E at Vn is equal to VDD. So let us observe the states of the transistors for these 5 ranges of inputs, so that what is the output value and how the transfer characteristics. See this table. Here 5 regions are represented, A, B, C, D, E, and the input values ranges condition, that is input is equal to 0 or it is less than of VTN, NMOS is off. So therefore 0 to VTN region 1, and VTN to VDD by 2 region 2, at VDD by 2 region 3, VDD by 2 to VDD minus mod VTP region 4, and Vin greater than of that VDD minus mod VTP as the region 5. So in these cases, let us observe the transistor on or off conditions. So first case, V in here, and this is a ground, and this is VDD. Here VGSN and VGSP are required. To know that, VGSN and VGSP. VGSP is VDD minus, VGSP is Vn minus VDD, and here VGSN is Vin minus ground. So the equations are VGSN is equal to Vin and VGSP is equal to Vin minus VDD. And this is the drain point and this is the source. So VDSP and VDSN. So this is the VDSP and this is the VDSN. Depending upon the values of this VGSN, VGSP, VDSP and VDSN, this inverter is having these 5 regions of equivalent circuits. First, let us take Vn is equal to in the first range where NMOS transistor is open. This is the region 1 or region A for the first case of 0 to VTN. Now, NMOS transistor is off, so open switch, and PMOS transistor is on, closed switch. Here, in this case, PMOS transistor is in the linear mode and NMOS transistor is in the cutoff mode. So, it's equivalent circuit. Then what is Vout? Vout is equal to VDD since there is no current. So, output is equal to VDD. Then in the second case, Vn is slightly greater than of VTN but less than of VDD by 2. So, means the both transistors are on and PMOS is in resistive or linear mode, NMOS is in saturation mode. The equivalent circuit is representing in this second region of region B like this. So here since both are on, current is existing, current is non-zero and output is reduced than the previous case, that is equal to VDD. So therefore output is less than VDD and it is greater than of VDD by 2. And the third case, when Vn is equal to VDD by 2, both transistors are on and both will be in the saturation region and its equivalent circuit is representing like this. Here IDSP and IDSN both are equal and both are maximum. So output is equal to exactly dropping exactly from output VDD to 0. So means Vout is dropping and Vout is equal to VDD by 2 only here. Exactly output is equal to VDD by 2. Then in the fourth region, that is input is having a greater than VDD by 2, less than VDD minus mod VTP. Then NMOS transistor is linear and PMOS transistor is in saturation region. So output is less than VDD by 2. And for the fifth region, when Vn is greater than of VDD minus mod VTP, NMOS transistor is on and PMOS transistor is off. And the two NMOS transistor is in the linear region. So NMOS is in linear, PMOS is in the cutoff. Since open path, it is having the discharge path. So output is equal to 0 and there is no current, it is exactly equal to 0. So this CMOS inverter circuit complete operation when input is changing from 0 to VDD gradually like this. 0, it is changing and it is reaching to VDD. In these regions also, what is output is represented here and what are the states of the NMOS and PMOS transistors are represented. Now by using this we can draw the characteristics of the CMOS inverter. Now CMOS characteristics, CMOS inverter transfer characteristics can be plotted like this with the help of the load line characteristics. So see the load line characteristics of CMOS inverter of particularly NMOS device and PMOS device. NMOS device characteristics will be like this. For the NMOS enhancement, IDS and VDS for a particular value of VGS, where VGS is equal to Vn. These are the characteristics for NMOS device. For the PMOS device, how the characteristics will be? They are in the third quadrant. Minus VDS and minus IDS. The characteristics will be like this. For the value of Vn only. So now, by superimposing these two characteristics only, we can draw the transfer characteristics from the intersecting points of these two load line characteristics. So for that, just first flip this and then shifting the PMOS characteristics, that PMOS characteristics will be represented over the NMOS characteristics. So these are the PMOS transistor characteristics and these are the NMOS transistor characteristics. So both are overlapped, and taking the intersecting points, the characteristics can be represented like this. So the intersecting points of these are the intersecting points of those points. That means when Vin is equal to 0, the NMOS enhancement transfer characteristic is this, and when Vn is equal to 0, the PMOS transfer characteristic is equal to this. Then the intersecting point is representing here, that is on the Vout axis it is equal to VDD. Therefore, output is representing as VDD value. Then similarly, Vin for the 0.5 of the NMOS and Vn for the 0.5 of the PMOS. Intersecting point of this, output is nearer to VDD. So that is output is representing nearer to VDD and it is for the 0.5 of the VDD. Like that, taking the intersecting points and we can draw the transfer characteristics of CMOS inverter like this. And in this graph, we can observe the 5 regions of operation of CMOS inverter. So the NMOS and PMOS regions are also mentioned. So this is the region C which we have seen, that is output is gradually decreasing, output is suddenly decreasing and output value is VDD by 2, and this is other regions, region A, region B it is, and region C it is, and region D it is, and region E at one point. Let us see this graph only like this. So all 5 regions. First region, then that is 0 to VTN is the first region. This is the region A, and VTN to VDD by 2 as a region B, and at to VDD by 2 that is region C, and VDD by 2 to VDD minus mod VTP that is equal to region D, that is this one, middle one, region D, and VDD minus mod VTP to VDD is the region E. So A, B, C, D and E, 5 regions. In that, output is equal to VDD and output is reducing from VDD to VDD by 2, and in the region C, output is equal to VDD by 2, then still it is reducing and finally it reaches to the 0. We have seen in the as a table there, and this is the characteristic of the voltage transfer characteristics of the CMOS inverter. And in these regions, how the NMOS and PMOS transistors are in the saturation or non-saturation are also represented. In region A, T1 is representing as NMOS here and T2 is representing as PMOS here. So in region A, T1 NMOS is off and T2 is in the linear region. Then similarly, in the region C, both are in saturation region and so on. Those are also represented here. These are the transfer characteristics of CMOS inverter. Now let us see, using the transfer characteristics, how the current is in the CMOS inverter. The current is maximum in the third region because both are in the saturation region, that we have seen in the equivalent circuits. See here, this is a region C. In the region C, both are in sat, so maximum amount of current will be flowing. And in the region A, since open, current is equal to 0, and region E also, since open, current is equal to 0. And in middle, region B and region D, the current is varying. So current is starting with 0 and it is increasing and it is a maximum in the region C. Then from the maximum it is reducing and again it will reach to 0 current in the region E. That is represented as graph, the current. The current in the region A is 0 and then it is slightly increasing and it reaches to maximum and it is reducing, and in region E it reaches to 0 again. 0, slightly increasing, and at region C maximum, and again it is reducing and finally it reaches to the 0. So that is current characteristics with respect to the Vin value. Current characteristics with respect to the Vin value. This is the current characteristics in the CMOS inverter circuit. Now, using these current characteristics, the two from the region C, maximum current characteristics, we are going to find the sizing of the transistors for getting the symmetric voltage transfer characteristics. So, sizing point. Sizing for the symmetric characteristics. Symmetric characteristics means what? Symmetric characteristics means, from this we can understand that. That is, for the region C, input value is changing from 0 to VDD. Here, the middle point is VDD by 2. This is the input. And output is, for this, coming the VDD to 0. Here also, the middle point should be VDD by 2. To get input VDD by 2, Vin is equal to VDD by 2, output is also VDD by 2. So, to get both voltages equal is called as symmetric characteristics. So, to get this, what should be the size of the PMOS and NMOS transistors? So, symmetric characteristics, we are going to calculate the sizing part. For that, we are taking the region C, where already we have seen V in is equal to V out is equal to VDD by 2 value. And in this region, both are in saturation and currents are maximum, and current IDSP is equal to minus IDSN. Write the equation part of IDSP and IDSN as saturation currents by following the saturation current equation. So, IDS's saturation current equation is beta by 2 into Vgs minus Vt whole square, where beta for the NMOS transistor is beta n and for the PMOS transistor it is equal to beta p. Beta n is equal to representation of K into W by L, where K is equal to epsilon naught epsilon insulator mu n by D and WL is represented as it is as Wn, Ln for the NMOS, Wp and Lp for the PMOS. Here changes mu n and mu p is also different for the NMOS and PMOS transistors. By taking these three and substituting IDSP and IDSN and equating it, we can get the sizes of the transistors. So, IDSP first. IDSP is just writing of VGSN minus VTP. VGSP is equal to what? VG minus Vs of the PMOS. At VG we have connected Vin. At source we have connected VDD for the PMOS transistor. So, Vin minus VDD is the VGSP for the PMOS transistor, minus VTP is the threshold voltage of the PMOS transistor. This is the IDSP. And IDSN is VGSN for the inverter is simply Vin minus source. Source is equal to connected 0. So, this is equal to Vin only. So, Vin minus Vtn whole square into beta n by 2. Beta p for the PMOS, beta n for the NMOS. Now, equate these two and rewrite and simplify it to get the Vn value. So, Vn is equal to this. Now, for getting the symmetricity, what should be the Vn? Vn is equal to VDD by 2. We have to get 0.5 VDD. To get that, assume beta n is equal to beta p and Vtn is equal to minus Vtp. Then we can get Vn is equal to 0.5 VDD. Therefore, Vn is equal to V out is equal to 0.5 VDD. So, by taking of this, For to get this symmetric value of V in, V out 0.5 VDD, our assumption is beta n is equal to beta P and Vtn is equal to minus Vtp. So let us take this beta n is equal to beta P value and simplify it to get the sizes of the PMOS and NMOS. So take the beta n is equal to beta P, beta n is equal to formula and beta P is equal to formula. Now by equating these two, D is the same, these two can be cancelled, epsilon insulator, epsilon naught can be cancelled. Therefore, mu n Wn by Ln is equal to mu p Lp Wp by Lp. This is the equation. Here, mu n and mu p are not equal and mu n is greater than of mu p and mu n is approximately 650 where mu p is 240. So, by substituting that, we can get it is approximately equal to 2.5 times of NMOS. So, PMOS size should be 2.5 times size of PMOS should be equal to minimum 2.5 times of size of NMOS to get the symmetric characteristics are V in is equal to V out is equal to 0.5 VDD. This is the conclusion from this. So the size required of the PMOS is equal to 2.5 times of the size of the NMOS as mobilities of the two transistors are not equal. This is the conclusion from the sizing part. And if the size varies, transfer characteristics varies. Let us see that how the transfer characteristics varies based on the sizes. First, let us take a characteristic with both transistor sizes are following the ratio of beta n is equal to beta p. In the sense what? PMOS size follows the NMOS size into 2.5. Then beta n by beta p is equal to 1. Means this is the symmetric characteristic where V in, V out both are equal at VDD by 2. Now if size is increased as beta n by beta p is greater than 1 means what? NMOS size is greater than PMOS size and taking as beta n by beta p is less than 1. That means NMOS size is lesser than PMOS size or PMOS size is greater than NMOS size. For these two cases. First, if NMOS is greater, then the characteristics will move inside. Means V invert point value is going to be decreased than this. And that means V invert is less than VDD by 2. If size of the PMOS is taken as greater, then V invert point is going to be increased. In the sense, V invert is greater than of VDD by 2. Means V inverting point can be V inverting. V inverting point can be changed or shifted to either lesser VDD by 2 or greater than VDD by 2 by changing the sizes of NMOS and PMOS transistors. So we can shift V invert by changing of NMOS and PMOS sizes. We can understand that characteristics variation with respect to the beta value. Let's check this quiz to get. Let's check this quiz to get a clarity of understanding of the CMOS inverter. In CMOS, if both transistors are in saturation, then they act as both transistors are in saturation. So we have seen that in region C both are in saturation and it is represented as equivalent circuit. What it means? It means it is a symbol for representation of current source. Therefore, answer is current source. Then in CMOS, if beta n is equal to beta p, then V invert is equal to, just now we have seen if beta n is equal to beta p, V invert is equal to VDD by 2. So the answer is 0.5 VDD. Next, in the CMOS inverter circuit shown, if the transconductance parameters of the NMOS and PMOS transistors are K and Kp values are given and threshold voltages are given, then the current is. So we have to find IDS for the given data. So let's take this as assignment question and solve how much is the current. And this also take as assignment question. That means taking the input value, changing its value from 0 to VDD, that is 5 volts. Understand the output value and mode of operation of NMOS and PMOS by varying the input values of these. Find the current IDS in this question. So both the transistors are in the saturation mode. Current equation is equal to IDS is equal to beta by 2 into VGS minus VT whole square, where VT is given as 1 volt and Kp and Kn, that is beta P and beta N directly given, that is equal to 40, and Vin value is given as 2.5 from the figure. So Vin is equal to 2.5 volts. Vt is given as 1 volt and beta P, beta N directly given as 40. So just substitute to find out IDS value, because in the at the value of 2.5 this is equal to VDD by 2. For the VDD of 5 volts, these two in the saturation mode, NMOS saturation mode and PMOS is also in the saturation mode. So saturation current is taken, just substitute here, that is 40 by 2 into VGS value is 2.5 for the NMOS minus VT value is 1 whole square. So 40 by 2 is 20 into 2.5 minus 1, 1.5, 1.5 square. So 20 into 1.5 square. That is the answer for the. So by taking a 20 into 1.5 square, 45 microamperes is the current, since this is taken as micro. We have taken 40 as the digit and micro, so 45 microamperes is the current. Since here IDS and IDP both are equal, I is equal to 45 microamperes. This is the answer for this question. Take this is also as a assignment question. Here typical CMOS inverter is represented with input value with transfer characteristics, and we have to find the value of the inverter threshold value, which is the input at which V0 falls by Vtn plus Vtp. So find this. Solve this question also as the assignment. Follow these two textbooks for the CMOS inverter operation, that is Essentials of VLSI Circuits by Pucknell and Neil Westate textbook by Principles of CMOS VLSI Design. The summary of this lecture are: we have seen CMOS inverter circuit, its operation, its transfer characteristics and its sizing of PMOS and NMOS transistors. I hope you understood the CMOS inverter. In the next lecture we will see bi-CMOS inverter. Thank you.